Now that we know how to break a vector down into its component parts, it's time to learn how we actually use that to improve the way that we can analyze our free body diagrams. Working with vector components helps us most whenever we have some sort of object on some sort of slope or incline. In this case, we have a downhill skier who is racing down a hill at a constant velocity of 33.5 meters per second. That's about 75 miles per hour. A downhill skier goes that easily during a race. We're going to use the appropriate problem-solving procedure to create a quantitative force diagram for the skier whose mass is 80 kilograms. Okay, so we have a lot of information on this page that we need to take a look at. First of all, constant velocity, very important. Then we also have a velocity here, and we're going to definitely use meters per second, even though we're given miles per hour. That's just to give us sort of an understanding of how fast they're going. And we have the mass of the skier, 80 kilograms. And we know that we want a quantitative free body diagram. That means every vector force arrow is going to have a number on it, which means we need to do calculations and then we need to think our way through the problem. First, we do create the free body diagram just like normal. We will circle the object, which is the skier, and then we're going to place any field forces, which would be gravity. I have that pointing down. I've kind of put a shorthand onto the notation here, so that'd be force of gravity on the skier by the earth. And then I'm going to place contact forces. Now, my major contact is right here at that surface, and so with surface forces, I need to consider both surface forces, the normal force and the frictional force. In this case, that normal force is going to be pointing in that direction at 90 degrees to that surface. And so I have force normal on the skier by the hillside or the surface, whatever you wanted to say, pointing in that direction. And then your frictional force is going to be parallel to the surface. And that always goes in the opposite direction of motion. So if the skier is headed down the slope, your frictional force is going to be in that direction upslope. And you can see that I have that drawn onto the free body diagram, force of friction on the skier by the slope or the surface. And that's your free body diagram. Now notice that in this free body diagram, we don't have any vectors that are directly opposing any other vectors. We don't have an up arrow that balances the down arrow of gravity. We don't have horizontal to the right, to the left vectors. And so what we have here is something that's kind of off kilter. And this is when vector components and breaking down the vectors helps us the most. Now, step 2 is to basically assign a coordinate axis system to the free body diagram. And this is so that we can begin to talk about which forces are acting in which directions, because as it stands right now, the normal force and the frictional force are just kind of pointing off at some angle. And, you know, it's going to get very complicated. If I just look at a straight, typical XY axis like that, that's vertical and horizontal, then the only force I have here that's going to be following an axis is going to be gravity. The other two forces I'm going to have to break down into its component parts. I'm going to have to calculate all of the different sides for the triangles I create. I'm going to have to do all of that. And I can, but I'm doing more work than I have to. Because the normal force and the frictional force are always at 90 degrees to one another, what I can actually do is I can take this coordinate axis system and I can just kind of rotate it a little bit. And you can see I've done that here, such that the y-axis no longer points straight up. It points up the normal force instead. So it's at sort of an angle to the vertical. And it's okay to do this. And that means that if the vertical y-axis is now kind of rotated to follow the normal force, well, then the x horizontal axis will now follow the frictional force. And I don't have to break those two forces down into their components now because they follow an axis. All I have to deal with is the gravitational force, which now doesn't. And so I've cut my work in half simply by rotating the axis like this. It's okay if not all the forces follow the axes. In general, rotating those axes so that the vertical y-axis follows the normal force is going to save you work. Step 3 becomes breaking down the gravitational force into its component parts. Now, we know that the angle on the hill here is 25 degrees. And if we look here, we can see that this angle here, made by the gravity vector with the vertical axis, is 25 degrees. Okay. If the hill is this orientation, meaning it's sloping from higher on the left to lower on the right, you're going to always use this angle that goes toward the axis that precedes it. And we can talk more about that in class. And what I'm going to do then is I'm just going to draw my vertical component, Fg, force of gravity in the y direction, down, and then I'm going to draw my horizontal component, Fg, in the x direction across to make a right triangle. And right there is that right angle that we know that we have to create between the component parts. Okay, now I've got my parts, okay, and I'm ready to move on. Okay, now I'm ready to do some basic calculations. The first calculation I'm going to do here is the actual force of gravity. That's the straight down vector that will become the hypotenuse of my right triangle. And right there's my right triangle. And if you take a look here, that's force of gravity equals m. That's the mass of the skier, 80 kilograms, and little g, which is 10 newtons per kilogram. That's the gravitational field strength of the Earth at the surface. And I get 800 newtons. I need to make sure that that's negative because my gravitational force vector is in the down direction, the negative direction. Then what I'm going to do is I'm going to take that gravity vector and I'm going to look at the components and I'm going to calculate the components. Because now I know that this is 800 newtons, negative 800 newtons. I can calculate, using my trig functions, I can calculate the magnitude of FGY and FGX. FGX, that is my horizontal component, is the opposite angle or opposite side to the angle, and that will be opposite over hypotenuse, which is the sine function. So I have FG sine of theta, or 800 newtons sine of 25 degrees. That's going to equal 340 newtons. If I look, this is going in the positive direction. This would be positive. This would be positive here. This would be negative. This would be negative. And my y component of my gravitational force is the adjacent side to that 25-degree angle. And so it will be Fg cosine of theta. That's 800 newtons times the cosine of 25 degrees. That's going to be 730 newtons in your calculator. But notice that that FGY is pointing in the down direction, so that one needs to be negative. You double check each component to make sure you're getting the correct sign based on what direction it's pointing in. Now, once I have those figured out, and give me just a minute, I'm going to fill those in. I have FGX at 340 newtons. I have FGY at negative 730 newtons. Then I just need to look at the rest of my free body diagram. Notice that my normal force is balanced by that y component of the gravitational force, by FGY. Equal in magnitude, opposite in direction, because the skier's not flying up off the slope and he's not sinking into the earth. And so what that tells me is that my normal force has to be equal in magnitude, opposite in direction. That means it must be 730 newtons positive, because FGY is 730 newtons negative. And if I look at my frictional force right here, because my problem tells me we're traveling at constant velocity, there has to be a force balancing that frictional force. And it is part of the gravitational force. It is this FGX, the force of gravity component in that horizontal direction that is equal and opposite to the frictional force. So if the force of gravity is 340 newtons positive, that frictional force has to be equal magnitude, opposite direction. It has to be 340 newtons negative. And this is a quantitative, fully solved free body diagram for that problem, using vector components to break the gravitational vector down into parts and then see how that gravitational vector, how its parts balance the other forces in the problem. This then would be your final free body diagram, okay? And that's just the same as what we did, except you've just put all of the numbers on there. Make sure with a quantitative free body diagram, all the numbers are all listed and labeled on the vector arrows on your free body diagram. And highly, highly, highly suggest you always use colors in some way for your components. It makes a huge difference in your ability to see what you're looking at. And we're done.